Hello and welcome again at the Academica Aqua Circular Conference. Um, Now we have another guest, Mr. Francis Meerburg. He's currently work as a researcher at Aquafin, the Flemish wastewater utility. Hello, Mr. Francis Meerburg. I want to test your microphone if you can hear me. I can hear you. Please check the microphone. Okay, now.
Can you hear me now? Okay.
Yes, I can hear you. I can hear you. Mr. Meerburg is, like I said, he's a researcher at Aquafin. Also, his work focuses around the recovery of resources like carbon, nitrogen, phosphor from used water, not wastewater, as well as decentralized water treatment solution. Mr. Meerburg today will talk about the implementation of circular economy initiative in the Belgian water sector and about the challenges and opportunities they faced. Mr. Meerburg, you please proceed your presentation.
Thank you. So, good morning. Thank you for listening. My name is Francis, and as the moderator said, I am working at Aquafin. What is Aquafin? It is the wastewater treatment utility of Flanders. And you might know Flanders is the northern part of Belgium. The southern part is Wallonia, and then there's Brussels in the middle. And so we treat the entirety of the wastewater of Flanders, which means 5.4 million people. We have lots of sewage pipes, pumping stations, and have a bit more than 300 wastewater treatment plants in the region. I was asked to give a presentation about circular economy in Belgium in the water sector. I'm doing my best to give examples of the whole of Belgium, but I will always refer to cases of Aquafin because those cases, those study cases, are the ones that I know best. I will talk about a few initiatives that have nothing to do with Aquafin. So I always use the word wastewater. This is my mistake because wastewater doesn't actually exist. We shouldn't speak about wastewater because what is a waste for one person or one company is not a waste, but is a resource for another company. These are a few examples of resources. So COD, which means organic matter, nitrogen, phosphorus, and potassium that are coming in our wastewater in the entirety of our 300 treatment plants every year. And as we see, this chart indicates the breakdown of what happens to these resources. Most of them are lost in the atmosphere as CO2, for example, or nitrogen gas. Some of them are lost in the effluent, and a big fraction sometimes, especially for phosphorus, is lost through the sludge. It's then incinerated. On the other hand, it makes sense to recover all of these resources because there are reasons why we should recover them. For example, if we look at the COD, it takes energy. There's a huge energy consumption needed to remove COD from wastewater. It also causes greenhouse gas emissions. If we look at nitrogen, it takes energy to remove it from the wastewater, but then it takes energy again to fixate nitrogen from the atmosphere to produce fertilizers, which is 1 to 2% of the total energy use in the world. That's huge. For phosphorus, there's resources. There's mines that are under geopolitical pressure. And for potassium, maybe that's the most urgent resource of all because we only have reserves in the world for another 100 years. So we need to come up with a way to recover that. And then maybe the most important resource of all is water itself. Wastewater is full of water that can be reused if it is treated properly. In this map, you can see the levels of water stress throughout Europe. And the more red this is, the more water stress we experience, as we can expect. The south, the Mediterranean parts of Europe are dark red. But also, if you look at Belgium, Flanders is actually extremely highly water stressed. That might be surprising. We have enough rainfall over a year, but we do consume a lot of water, which results in high water stresses in Flanders. And I also noticed that in Romania, there's regions that have an extremely high water stress. So what I'm saying at this moment in this presentation is probably applicable to Romania. And you might have seen this principle somewhere else, but the message that I'm giving in this presentation is that we need to move from a linear chain of resources that are used only once in our economy and then wasted or disposed as waste in the end, to a circular chain where resources are reused at different locations within the chain, and at different scales, from a household scale to a cluster or a municipality or even a national scale. A few examples of resources that are being recovered or that can be recovered from wastewater. To start, phosphorus. Phosphorus recovery is pretty simple actually, because phosphorus has a fairly easy chemistry. It can be precipitated into crystal form, or it can be recovered from incineration ash. If you incinerate the sludge, you can leach out phosphorus and produce a concentrated solution of phosphorus that can then be reused as fertilizer. Phosphorus recovery in wastewater can happen at different scales or at different sites within the cycle. If we start with pure urine, this is an easy way to recover phosphorus. So if you have, which is called source separation, you separate urine from the other streams of wastewater. You have a fairly pure stream full of nitrogen and phosphorus that can be easily recovered. There are examples. These are all pictures of aquafin installations. Examples of recovery installations for phosphorus on the centrate, on digestate of digest sludge. And we're also planning a full-scale phosphorus recovery on the ashes of incinerated sludge by 2026. The next resource that I will talk about is carbon. Organic carbon, or COD, as we express it in wastewater. It's actually a very complex molecule because there are so many different forms of organic carbon that can all be recovered in a way. These are a few examples of what's happening in full scale already throughout Europe, not only Belgium, but Europe. So cellulose from paper can be recovered as paper fibers to produce new paper. Bioplastics that are biodegradable, alginate, compost. There's a whole suite of different components that can be recovered from organic carbon. Those of you that are familiar with the Volatile project know that we can recover VFAs, so volatile fatty acids, from carbon from the sludge. But also all of these examples, bioethanol, biochar, CO2 itself, humic acids, microbial proteins, etc., etc. These are at different levels of application. Some of them are in the pilot scale stage. Some of them are only in the lab stage. But there is always a trade-off between recovering carbon as a product or recovering as an energy carrier. Carbon is a carrier of energy, and if you incinerate carbon, you produce heat or electricity. And so for Aquafin, we are actually focusing mostly on recovering carbon as energy and not as a resource. So this can be done in two different ways, either internally in the plant by optimizing the energy balance of the treatment plant, producing biogas and boosting the production of biogas and recovering electricity by incinerating the biogas, or externally by treating the sludge. So the waste sludge of the treatment plants can be treated in thermal ways, so just incineration, or more novel technologies such as supercritical oxidation or pyrolysis, or things like that to recover energy from the sludge. I will talk about energy a bit later on in this presentation if there's still enough time. Another resource is the nitrogen. This is a funny resource because there's actually no shortage of nitrogen. The atmosphere is full of nitrogen. We can recover it by simply fixating nitrogen on an industrial scale to produce fertilizers. It is not difficult to recover nitrogen from wastewater either. It's mostly a question of energy. It takes a lot of energy to recover nitrogen from wastewater because it is mostly done by stripping ammonia from the wastewater and then precipitating it again to produce a concentrated solution. So recovering nitrogen is always a question of balancing energy needed to recover it versus the energy that is needed to remove the nitrogen and then fixate it again to produce fertilizers. To boost this development a little bit more, we are planning a demonstration project to recover nitrogen from centrates in our treatment plant, one of the treatment plants we have in Antwerp. And then finally, as I said, the most important resource of all of them is water, water itself. If we treat wastewater, we produce an effluent. This effluent can either be used directly for low-grade applications, or it can be further processed and treated to use even drinking water or high purity industrial waters. And I will give a few examples of what's happening in the case of water recovery. First of all, if we look at the water balance, this is a balance of water consumption and water sources in Flanders, but this is applicable to all of the European countries in a way or another. We see that we consume a lot of water. We consume a lot of water for personal hygiene. So that means showering, wash basins, bathtubs. We consume a lot of water for toilet flushing. And then there's laundry, food and drinks, and a few other uses of the water. And the source of our water consumption is mostly tap water. There is a little fraction of rainwater for households, for example, who have a rainwater tank to use for toilet flushing, for example. But most of the water we use is always tap water. While we don't actually need drinking water, potable water, for all of these applications. Obviously, for personal hygiene and for food and drinks, we need potable water, but we do not need to flush the toilets or do laundry with potable water necessarily. So we should rethink this cycle. How can this be done? This is my personal opinion on how we should deal with the water cycle. I will walk you through this scheme. So first we have tap water. Tap water or potable water should only be used, in my opinion, for applications that need potable water. So that means everything that we come in contact with people. You come in contact with taps in the kitchen or in the bathroom. We come in contact with the shower water, and obviously we drink the water as well, and we use it for food preparation. So we need potable water for that. The wastewater that comes from these fractions in the household is called gray water, and this can be treated locally. So that we have a source of treated gray water that is not potable, that we can use for other applications such as laundry, toilet flushing, cleaning, maybe gardening, etc. The wastewater from these applications is called black water, and this can then be recovered or treated in a central facility, so that we can actually use every drop twice. Every drop of water is used twice. What happens to the rainwater? Well, nothing actually. In the ideal situation, we don't need rainwater, and we can simply let it infiltrate in the ground, so that we have enough groundwater level to produce again tap water. This is an example of a location where we do where we actually are using this scheme. It's called the Kruidfabriek, the Gunpowder Factory. It's a location near Brussels where we are taking the gray water that comes from kitchen and sinks. We are treating this on site in a constructed wetland, and then we purify it further in a nanofilter, and we reuse it for toilet flushing, or it is used at the garden as well. It is used for a bicycle repair workshop, etc. We also recover phosphorus sulfide from the urine also. I'll skip this slide. And then, so not only Aquafin, but other companies throughout Belgium, throughout Europe, are starting with lots and lots of initiatives for local treatment of water, decentralized treatment, decentralized production of drinking water. There's lots of examples. This is an example of a mobile treatment unit that treats festival wastewater, because festivals that are often organized in the field don't necessarily have a good water treatment. So with this solution, we can drive to the festival and treat the water locally. A very interesting example that I wanted to share with you is the new docks, or the Nieuwe Dokken in Ghent. If this is interesting for you, I recommend to look up their website. It's a very interesting project. It's an example of a circular neighborhood that is in close collaboration with a nearby factory, and waste from one of these players. So the waste of the factory is heat. The factory produces lots of waste heat. This is used by the neighborhood for district heating, and then the waste of the neighborhood, the water, is purified locally and is used by the factory again as a source of processed water. Another example is the use of our effluents. So in our central treatment plants, we produce purified wastewater, or effluent as we call it, which is discharged into the environment. Right now, this is not used very often. Sometimes a farmer comes to our facility during a drought in the summer to collect some water for their fields. But we want to move to a more standardized approach where we actually have control over the safety. We know about legislation and the treatments that are needed for farmers to reuse our effluents. And the new European directive on wastewater reuse is really going to help. Industries are using our effluent. They're using lots of our effluents, actually. For example, this is an example of a compost installation or a chemical factory. But then the most important example is the treatment plant, the drinking water plant of Wilpen. I'm not sure, it's in Kokzijde, near the coast of Belgium. Not sure if you've heard about this, but this is a plant that has been operating for 20 years, and they do indirect potable water reuse, which means that they are taking our purified wastewater, so the effluents of the treatment plant. They are producing drinking water out of this, infiltrating it in the dunes for a little while. So only 100 meters after the infiltration site, it is extracted again. And it is produced. It is used for drinking water production. This is one of the prime examples of potable water reuse in Europe. This has actually been a unique plant in Europe for the last 20 years. Right now, there's a few other initiatives on potable water reuse happening all around Europe. This was a very early adopter of this scheme. Finally, I'm not sure if time permits. I promised to talk a little bit more about energy. I will go quickly over it. As I said, Aquafin is mostly planning to use carbon in the wastewater for energy optimization rather than recovering the carbon as a product. So, well, this was an animated slide. It's not animating, but it's not a problem. So what can we do to boost self-sufficiency of a plant? If you look at a scheme of a conventional treatment plant, these are the blue boxes. We have aeration, secondary settling, dewatering. What can we do to recover energy? Well, the first and the most important step is add an anaerobic digestion, so that you can produce biogas. And to boost that biogas production, there's different things that we can try. So we can have side stream treatment, NMOX, to remove nitrogen in the side stream. We can add a primary settling phase. We can do a thermal hydrolysis. And if we add all of these technologies to the treatment plant, we end up with an energy self-sufficiency of about 56%, which means we can recover, or we can produce 56% of the electricity that we actually need to operate the plant. If we want to go any further than that, we need to rethink the whole treatment cycle, or we need to import external energy, such as this example in Tilburg in the Netherlands. This is an energy positive plant, so they actually produce more energy than they need, because they are able to import a lot of external sludge, which is an energy carrier, of course. Aquafin is planning to increase its energy self-sufficiency to about 50% by at this timeline by 2040, and we can do this by boosting the internal production of energy, not just biogas but also solar and wind, on the one hand, and then on the other hand, reducing our overall consumption of energy by being more efficient over the years. We're also doing, we also have a pilot plant in the running for producing biomethane, so upgrading biogas to a purified form of methane so that it can be injected in the gas grid. And this, I think this is the final example, my final slide, is an example of a new housing project that is planned next to the treatment plant of Deurne in Antwerp, where we are planning to recover heat from the wastewater. You may know that wastewater is always a few degrees warmer than the environment because water is heated in households. And so it makes sense to recover heat from wastewater before or after the purification process. And so for this new housing project, we are planning to start a district heating system where we are recovering waste heat from our sewer systems. And by that, I will finish my presentation. I think the picture is gone, but this should be a picture of me. This is my contact info, so please contact me if you have any questions. And I will happily answer questions here in the chat if you have any.
Okay. Thank you very much for your presentation. Now I would like to start the question session. If there is any question, we have 2 minutes left, around 2 minutes left. If there is one question, we can answer at one question. Okay. Yes, we have question, please. Florica Mane asks, do you have experience with separate collection of gray water and black water? If yes, which is number of PE? Which are the main challenges?
Okay, thank you for the question. We have a few demonstration projects in the running where we are treating gray water separately. The example that I was showing of the gunpowder factory near Brussels is an example of that. So we separate the black water of the toilets from the gray water of washing basins and kitchen. We only, so in terms of PE, so population equivalence, we only have demonstration projects for a few households. So that's, you know, maybe between 10 and 20 PE, not too much. I think to answer your question on a more broader scale, if you would move to a larger infrastructure, so a whole housing project, for example, or a whole neighborhood where they separate gray water and black water separately, the most important problems that you would run into are, I think, it's solids from the kitchen that are clogging the pipes. Maybe eggshells that are clogging the pipes. If you also allow people to put green vegetable waste in their kitchen sinks, which is always done in comparison, so in combination with black water treatment, because it makes sense. And I think the other challenge would be economical. It is expensive to put piping in the ground. If you want to develop a neighborhood with a dual piping system, so a separate black water and gray water piping system, it will cost much more money. And the question is, does it make sense? Can we recover that extra investment by making money somehow in another way? And that's the biggest challenge. We are involved in a few cases where we are just calculating economical balances for new neighborhoods, and it's always the economy of the piping system in the ground that is the biggest bottleneck.
Okay. Thank you very much. We don't have another question, and the time is end now. So thank you very much for your presentation, and we invite you to watch, to follow our next webinars. Thank you very much again.
Okay, thank you. See you.
Bye bye. Bye
Bye.
bye.